Welcome to our complete walkthrough of LeetCode problem number 300, titled Longest Increasing Subsequence. In this video, we will explore multiple solving strategies, break down example cases in detail, analyze complexity, and provide full code explanations in both Python and Java. By the end, you will deeply understand how to tackle this classic dynamic programming interview problem and why it is important for real-world technical interviews and coding assessments. For LeetCode problem number 300, we are given an integer array named nums. Our task is to find and return the length of the longest strictly increasing subsequence. A subsequence can skip elements, but the order must remain. Importantly, elements must be strictly greater than the previous to form the increasing sequence. For example, in the array 10, 9, 2, 5, 3, 7, 101, 18, the longest increasing subsequence is 2, 3, 7, 101, giving us an output of 4. Notice how we skipped numbers to form the sequence but kept their original order. In another case, with input 0, 1, 0, 3, 2, 3, the longest strictly increasing sequence found is 0, 1, 2, 3, also with length 4. When the input is 7, 7, 7, 7, 7, 7, 7, since all elements are equal, any single element counts as an increasing subsequence. The answer is 1. The constraints ensure reasonable input sizes, with the array holding between 1 and 2,500 elements and values between -10,000 and +10,000. Edge cases include a single element array, which always has a longest subsequence of 1. If the array is strictly decreasing, like 5, 4, 3, 2, 1, only one element can start a strictly increasing sequence, so the answer is 1 as well. Arrays where all elements are identical return 1, since no element is strictly greater than another. When approaching LeetCode problem number 300, there are several strategies you might consider. The classic method uses dynamic programming, building an array where each position stores the length of the longest increasing subsequence ending at that position. For every index, you scan all prior elements to see if an increasing relation exists and update the length. This approach is easy to implement but runs in quadratic time. A more optimal solution uses binary search and a cleverly maintained sequence array. For each number in nums, you locate the appropriate spot using binary search to either replace an existing value or extend the array. The size of this array at the end represents the length of the longest increasing subsequence. This method achieves n log n time complexity, but can seem less intuitive initially. Greedy approaches do not suffice for this problem, as making local choices does not guarantee the longest possible sequence. In summary, while dynamic programming provides clarity, binary search-based optimization is best for overall efficiency when arrays are large. Your choice will depend on requirements, constraints, and interviewer preferences. Let's break down the binary search-based algorithm for LeetCode problem number 300 step by step. First, we create an empty list called seek. As we iterate through each number in the nums array, we compare number to the last value in seek. If number is larger, we extend seek by appending number, representing a longer increasing subsequence. If number is smaller or equal to some element in seek, we use binary search to find the first position where it can replace a value. This ensures that seek always maintains the smallest possible tail values for increasing subsequences of different lengths. A critical insight is that seek does not preserve the actual sequence, but its length at the end is exactly the answer we need. By always trying to keep seek as small as possible and replacing larger values, we leave options open to create future longer sequences without violating the problem's definition. This technique also guarantees that the resulting length is correct while providing the best efficiency possible. The Python implementation for LeetCode problem number 300 begins by importing the bisect module, which provides efficient binary search functions. In the solution class, we define length of lis, accepting the input list nums. We maintain an empty list called seek. For each number, we use bisect_left to locate the insertion point. If the position is at the end of the list, we append number, as it extends the sequence. Otherwise, we replace the existing value, ensuring the sequence's minimal tail property. Finally, the length of seq is returned, giving the longest increasing subsequence length. This method is efficient and concise, leveraging Python's built-in tools. For LeetCode problem number 300 in Java, our logic remains the same. We use an array list named seq to hold the increasing subsequence tails. For each number in nums, we use collections.binary search to locate the position. If binary search returns a negative value, we convert it to the correct insertion index using POS1. If the index equals the current size, we append number, otherwise, we replace the existing item. The final result is the size of seq. Java's static typing and exception-safe code structure ensure robust and maintainable solutions, though the syntax differs from Python. Let's step through the algorithm for LeetCode problem number 300 with detailed examples. Using the first input, 10, 9, 2, 5, 3, 7, 101, 18, we start with an empty list. We add 10 to seq. When 9 appears, it's less than the tail, so we replace 10 with 9. For 2, we again replace, getting 2. Next is 5, which is larger, so we append. As 3 comes, we use binary search to find out it replaces 5, forming 2, 3. For 7, it gets appended. 101 is much bigger, so we append. The last number, 18, replaces 101 in the last spot. Ultimately, the seq list shows 4 elements, corresponding to the answer 4. For input, 0, 1, 0, 3, 2, 3, repeating this process yields a maximum subsequence length of 4, as expected. This hands-on breakdown clarifies how the algorithm updates its state at each step for every element. Analyzing LeetCode problem number 300, the binary search algorithm runs in O(n) log n time. As every number in nums is processed, a binary search is performed on the sequence array, which may have at most n elements. In contrast, a naive dynamic programming solution requires 2 nested loops, resulting in O(n) squared time. Space complexity for both approaches is O(n), as we need to store sequence information or DP tables for up to n elements. In practice, the binary search approach is preferred for large arrays since its efficiency scales well. However, the DP method is sometimes easier for beginners to grasp and implement, especially in interviews where clarity may be valued over absolute speed. Knowing both methods allows you to adapt to different scenarios and interviewer preferences. LeetCode problem number 300 relates closely to several advanced interview questions, including Russian doll envelopes and wiggle subsequence. These problems can extend or alter the concepts found in the longest increasing subsequence problem. Common pitfalls include mixing up subsequences and subarrays or not paying attention to strictly increasing requirements. To optimize, leverage binary search within the sequence array, and practice dynamic programming to solidify understanding. In interviews, always be ready to explain both O(n) squared and O(n) log n avenues and proactively handle edge cases. Sometimes you may be asked to print or reconstruct the actual subsequence. Be prepared with a plan. By mastering these skills, you'll approach technical interviews with confidence, ready to handle a wide variety of dynamic programming challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!